All right, lesson 7-3. Let's see if I can make this shorter than the last one, huh? You know that the sum of the angles of any triangle at all, is always 180 degrees. So what about polygons that have more than three sides? What, for instance, about a quadrilateral? Well, a quadrilateral, excuse me, I need to get to, or I can use this pen. Quadrilateral, any quadrilateral's got four sides to it. That's the meaning of the word quadrilateral, four sides. Suppose we draw a line from one vertex of that quadrilateral and split that quadrilateral into two triangles. Certainly this could be done with any quadrilateral. And then I label all of the angles A, B, C, D, E, and F. I've got 6 angles in there. 3 of those angles belong to one of the triangles, and the other 3 of those angles belong to a separate triangle. But altogether, those 6 angles, the A, the B plus the C, the D, and the E plus the F, those 6 angles taken together really comprise the 4 original angles of the original quadrilateral, right? This one angle of the quadrilateral, I've just kind of split into 2, not 2 equal angles, but just divided it into 2 pieces, one seemingly larger than the other. Same with this angle in this corner here, okay? But for sure, since the angles of any triangle add up to 180, we know that angle A plus angle B, which is just this right here, and then angle F plus that right there, those all add up to 180. And we also know that C plus D plus E, those 3 angles, C plus D plus E, that also adds up to 180. So what then is the sum of A plus B plus C plus D plus E plus F, all 6 of those angles? What are they going to all add up to total? They're going to add up to a total of 360 degrees. Or here's another way to think of it. Since I divided this quadrilateral into 2 triangles, okay, and each triangle has 180 degrees worth of angles in it. 180 degrees per triangle times 2 triangles is 360 degrees. Now that's for any quadrilateral. There's nothing special about this quadrilateral at all. Clearly it's not a square or a rectangle or a parallelogram. It's not even a trapezoid. It doesn't even have one pair of parallel sides. There's nothing special about this at all. It could be any kind of quadrilateral whatsoever. The sum of its interior angles, the angles on the inside, would have to be 360 degrees. Now we can do the same sort of work for a 5-sided polygon, a pentagon. I'm sure you've heard of the Pentagon, just outside of Washington, D.C., right? Big 5-sided building, which houses a lot of our military operations, right? The Pentagon. Or, a pentagram is a 5-pointed star. Pent for 5, the pentathlon. You're probably not familiar with the pentathlon. It exists. It's 5 events. And 5 events you probably couldn't possibly guess exactly what they are. Google it. Might be interesting. Anyway, we take a pentagon, do the same thing. From one vertex, kind of carve out one triangle over here. There's going to be 180 degrees worth of angles in that triangle. And then from that same vertex, carve out another triangle, D, E, and F. And actually, that diagonal there has the effect of carving out 2 additional triangles. So now we have an angle G and an angle H and an angle I. And so we've got 3 triangles that we've carved out of this pentagon, and each one of those triangles has 180 degrees worth of angles in it for a total of 540 degrees between that angle, that original angle of the pentagon, that original angle of the pentagon, this one, and that original angle. A pentagon has 5 sides and it has 5 angles. Okay. always a polygon has the same number of angles as it has sides. And the sum of those 1, 2, 3, 4, 5 angles will always be 540 degrees. It does not have to be a special kind of pentagon in any sense. We can keep doing this. For hexagons, carve a triangle out of there, carve another triangle, carve a third and a fourth triangle. I've got 1, 2, 3, 4 triangles there that can be carved out of a hexagon. There are 180 degrees worth of angles per triangle times 4 triangles, 720 degrees. So the total of all of these angle measures, watch. This one, that one in the original hexagon, that one, there's a third, there's a fourth, there's a fifth, and there is a sixth. Sum of those 6 angles always going to be 720 degrees. A heptagon is 7 figures. We're going to get 5 triangles out of that. 180 times 5 is equal to 900 degrees. Now, this is what we do in mathematics. We generalize our results. Okay, and we say, well, what about a polygon with n sides? And we call such things n-gons. Literally, that's the name for a polygon that has some number of sides. We don't know what it is. We want to let it be just some random number. We call it an n-gon, which means it has n sides. Now, look at the pattern in these first 2 columns here. When I have a 4-sided polygon, I can carve it up into 2 triangles. 5-sided polygon, 3. 6-sided polygon, 4. 7-sided polygon, 5. Can you give me an algebraic expression for the number of triangles I would get out of a polygon with n sides? You see the pattern here? How do we express that algebraically? It would be n minus 2, wouldn't it? And again, do you see the pattern here? 180 times 5, 180 times 4, 180 times 3. It's always 180 times whatever that number of triangles was. And so in this case, polygon with n sides, it's going to be 180 degrees times n minus 2. And you can't come up with a number for that because we don't have a number for n. Okay, that's it. That is a formula then for the total number of degrees, the sum of all of the angle measures in a polygon with however many sides we want, right? And this is the way the formula is written. The sum of the interior angles. It's capital S, a lowercase I, which is written usually as a subscript, like slightly below the line, right? The sum of the interior angles of a polygon is equal to 180 times n minus 2, where n is the number of sides in the polygon. And this works for a polygon of any number of sides, including a triangle. Okay? I mean, we could test it for a triangle. The triangle has how many sides? 3. Put 3 in for n. We get 3 minus 2 is 1. 1 times 180 is 180, which is the answer that we would expect because we already know a triangle's angles sum up to 180 degrees, right? So this is a formula that you don't have to memorize because we're doing all this remotely, but you have to know how to use it, okay? And it might seem like a fairly easy formula, but we're going to get into some examples that I think if I didn't show you some examples, you might be quite stumped as to how to work through some of these problems, okay? And by the way, little detail here, we use the subscript I here because there are such things as what we call external angles of a polygon, as opposed to the or exterior angles of a polygon, as opposed to the interior angles, the ones on the inside. For instance, if you have, well, let's look at this heptagon right here, this 7-sided polygon. The way you create an exterior angle is by extending one of the lines, one of the sides of the polygon. And then the angle that that extension forms with the next side of the polygon, that angle that's not inside the polygon. That's outside of the polygon. It's called an exterior angle. And we have formulas involving the sum of the exterior angles also. We're not going to talk about those this year. It's one of the things that we're just skipping. But that's why this formula, this capital S, has a lowercase I written next to it. If there wasn't a difference between interior and exterior angles, or if exteriors didn't even exist, we wouldn't need that little I there. But that I stands for interior, okay? So let's move on to some examples. First one couldn't be any easier. Find the sum of the interior angles. That's exactly what this formula gives you when you know the number of sides. You plug the number of sides in here, and the output then is the sum of the interior angles. A decagon, that's something I expect you to know. Come on, you're familiar with the words decade. It's got 10 years. Decathlon is an Olympic event. It's got 10 events in it. The word decimal, DEC, talks about tenths and hundreds and thousands, which are powers of 10, right? All of these words beginning with DEC, the prefix is DEC, they all mean 10. So a decagon, I would expect you to know that that has 10 sides. I also expect you to know a pentagon has 5 sides. I expect you to know a hexagon has 6 sides. Okay. Of course, these are things you could all look up, right? But these really are things you should know. Hexagons are quite common, both in artwork, in construction, and in nature. Came across a really interesting article one time about honeybees and the way they build their honeycombs. And all of the cells of a honeycomb are in the shapes of hexagons. And there's a reason for that. Very interesting. Anyway, octagons, you know what an octagon is. An octopus has 8 legs. An octagon has 8 sides. Okay. A decagon. And there's all other kinds of names for weirdly... Heptagon is 7 sides. Nobody knows what that is. I'm not going to ask you to know a heptagon. Or a nonagon, which is 9 sides. I don't care. In any case, you can look all these things up, right? So to find the sum of the interior angles of a decagon, which has 10 sides, we just got to plug 10 in for n. That's all. And then simplify. 10 minus 2 is 8. 8 times 180 is 800, and 640 is 1,440 degrees. There's the answer to the question. Easy. Could not be any easier. At which point now you're thinking, all right, I'm going to turn this video off. Don't. Okay? Because now come some questions that are not as easy as that. Okay? Although this one really shouldn't be that much of a stretch. The next question, 1B, which means it's coming from question 1. It's a second part. If the decagon, okay, this 10-sided polygon, was regular, okay? I didn't talk about that word on the previous page. In geometry, when we talk about a polygon being regular, we mean that all of the sides are congruent and all of the angles are all congruent, okay? So for instance, a square is a regular quadrilateral because it has 4 congruent sides and it has 4 congruent angles. A rectangle has 4 congruent angles because they're all right angles, but it does not have 4 congruent sides, so it's not a regular quadrilateral. And a rhombus, by definition, has got 4 congruent sides, but it does not have to have 4 congruent angles, so it is not regular. And by the way, the meaning of that word regular shows up in other contexts, not just geometry, where it means sameness also. For instance, if somebody is, say, reporting to the police, as a witness to a crime, he says something like, well, I heard like 5 shots fired at regular intervals, And what does that mean? I heard 5 shots fired at regular intervals. That means the regular means the same, and the interval is a gap between. There's the same time between shots. That's what he's saying. 5 shots fired at regular intervals sounds like this: bang, 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 as opposed to irregular intervals, which might sound like this: bang, 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 right? Not the same time between each. So that word regular, that's a useful word to know, okay? So back to the problem now. if the decagon was regular, all the sides are the same, all the angles are all equal, what would the measure of a single interior angle be? Oh, you know what? I'm just realizing here that the answer to the previous question I wrote incorrectly. It's 1,440 degrees. Okay? That's the total of all the interior angles. And there's 10 of them. And what if all 10 of them are the same? How much is one of them going to be? Well, isn't it going to be 1,440, which is the total, divided by however many angles there are? Total degrees, number of angles. 144 degrees per angle. Now, you don't have to write the phrase per angle in your answer because I've asked you, what is the measure of a single interior angle? 144 degrees. That's a good enough answer. Okay. This is really just applied arithmetic, isn't it, at this point? I mean, this doesn't even have anything to do with geometry. Okay. If you know, for instance, if our class of 25 people, if I'm going to distribute 600 candies total to all 25 students, and everybody gets the same number of candies, you're just going to divide 600 candies by 25 students, right? That's just applied arithmetic, right? So if you know the total number of degrees in a polygon for all the interior angles, and you know that all the interior angles get the same number of degrees, you're just going to divide the total by however many angles there are. Now, I'm going to give this to you in formula form, but I don't know that you really should need this formula for a problem like this, okay? But here's what the formula looks like, and you could find this online and in math books. Capital I, that stands for a single interior angle measure of a polygon. That would be the total number of degrees, which we already know is 180 times n minus 2, divided by the number of angles that there are, okay? Sometimes I like to put a little subscript R below that capital I to stand for regular, an interior angle measure, one interior angle measure of a regular polygon, okay? I mean, if we don't know that all the angles are the same, then we can't do this, and I don't know what we could do, all right? So there's a formula that, again, I don't really think you ought to need for a problem like this, but it doesn't hurt to have it, okay? I've got it highlighted in the finished version of the notes. Number 2, let's move on. The sum of the interior angles of a polygon is 2,520 degrees. I'm giving you the sum of the interior angles this time. Okay. This question is basically going backwards. I'm asking you how many sides. In this first question, I gave you the number of sides, 10. I asked for the sum of the interior angles. Now we're going backwards. I'm going to say this 1,000 times next semester because we have so many formulas to work with next semester. This semester, we've hardly had any formulas at all. In fact, this may be the very first one. Well, other than, I suppose, formula for the midpoint. Okay. What you should do anytime you're solving problems with formulas, you got a problem and you know there's a formula related to the problem, you should write down the formula. And when I say write down the formula, I mean the whole formula. And what I mean by that is there are two sides to a formula and an equal sign between the two sides. Here's what I see all the time from my students when I start saying this. Isn't there a formula for this problem? Mr. Nortillo, I'm stuck. How do I do this problem? I say, isn't there a formula? They go, yeah. I say, write down the formula. And all they write down is the right-hand side of the formula. They don't write down the left-hand side or the equal sign in between. And I say, that's not the formula. And now they think they have the thing completely wrong. They don't. They just haven't written the whole formula down. And here's why it's so important. If you don't write down the left side of this formula, if you just write down the right side, you will have no idea how this formula is going to help you solve this problem. You'll be completely stuck, okay? Whereas if you write down the whole formula, then I can say to you, now, the information you've been given, where does that go in the formula? What does it stand for? What does the problem tell you it represents? Well, the problem tells you that this 2520 is the sum of the interior angles. And so it gets plugged in here, not there. Okay? Students who don't write down the left side of the formula would probably plug 2520 in for the n. Or maybe they'll realize, no, wait a minute, that doesn't go there. But they won't know what to do with that 2520 because they don't have a place for it because they didn't write down the whole formula. So if you put the 2520 in there, equals 180 n minus 2. Now you got an equation that's just got one variable in it. That variable does in fact stand for the thing I'm asking you to find, the number of sides in the polygon. We just got to do a little algebra here to solve this equation. Now, I know most of you would probably distribute the 180 because students love to distribute. Whenever they see a chance to distribute, bam, they distribute because they know how to do it. They can do it right. They're confident. But that's not how I would solve this equation. You can, it's totally fine. And in the completed version of these notes, I could show you how you can solve this equation by distributing the 180. But it's fewer steps, shorter amount of time if you start not by distributing the 180, but dividing both sides by 180. Yeah, I know you're going to have to reach for your calculator to do that, but you would have had to reach for your calculator at some point anyway. All right? 2520 divided by 180 is 10, let me see, 1800, 714 is 14. Yes. 14 is equal to n minus 2. And now there's one thing left to do. Add 2 to both sides. 16 sides in the polygon. Okay? There are problems like this on the homework. Maybe you'll need to refer to this example in the notes to do one or two of them. Okay? And then there's this problem here, the measure of a single interior angle. Single one is 168 degrees. Okay? Imagine that. And it's a regular polygon. Polygon that has an angle there, it's 168 degrees, and then another angle that is 168 degrees, and then another angle that's 168 degrees. It's probably going to take an awful lot of sides for this polygon to kind of circle around back to where it started. How many sides is the question? Okay. Now we have this formula, SI equals 180 times n minus 2, but there is no place in this formula for the value of a single interior angle. But there is this other formula, right? That's not on the front note page, but here it is. We sort of got it out of this example problem here. And that has a place for the measure of a single interior angle. So that formula would be worth having on hand while you're doing the homework tonight also. For sure, there are going to be problems like this one, number 3. I'm going to recopy down the formula. The measure of a single interior angle is 180 times n minus 2 divided by the number of sides. Again, you write down the whole formula, not just one side of it, and then ask yourself, the information I've been given, what does it represent? Where does it go in the formula? Well, it goes in here. 168 is equal to 180 times n minus 2 divided by n. And again, I'm sure the instinct for many of you would be, let's distribute that 180. We are going to end up doing that to solve this problem. We will. There really is, there's no way around it. Okay. In the previous problem, I avoided distributing the 180 because I could. In this problem, there is no getting around it, but I still don't want to do it first. Okay. The real important step, and you're going to have to do this step at some point, I think it's just as well to do it now rather than later, is multiply both sides by n. I don't know how many of you would think of doing this. You want to get this n here out of that denominator. And you're going to multiply both sides by n to do that. Okay. The result now, n times 168 is 168n is equal to, and you still have this 180 times n minus 2. Now is the time for distributing the 180. We don't want to divide both sides by 180 because this is not a constant number here. It's 168n. Okay, so we really do need to distribute the 180 now. 168n is equal to 180n minus 360 when you distribute the 180. If it were me, I would subtract 180n from both sides, even though I can see in advance that's going to give me a negative n on the left. I don't care because I'm comfortable with negatives, and besides, I got a negative 360 on the right. So I got negative 12n is equal to negative 360 if I'm just going to recopy that over here. If you divide both sides by negative 12, then you get n is equal to, negative divided by negative is a positive 30. There are 30 sides in this regular polygon. I would not be able to draw a regular 30-sided polygon if my life depended on it. Not one that would look good, certainly, which is why I did not draw such a picture for this problem. Okay, that's the lesson. Have these examples available to you. I got a really nice, clean, completed version of these notes. And I would recommend having these notes out while you're doing the homework problems. I wrote out the solutions to pretty much all of them, but not every last one. Okay, there's one problem, I think the last problem, I gave the answer for without showing the work. But what I put in the answers was the work for this problem is just like the work for, and then I referred to some other problem. Okay. And if you have questions about any of it, we can talk about it in class with me or whoever your teacher is. All right, that's it. Go do the homework.